Well, so here we're going to go to the second video here. So I'm going to stick with the YouTube live streaming, but to make it more exciting, I've added some background music, which I'll shut off pretty soon because it's really annoying. So, just as an FYI. I don't know why, but this is a song called Finite Element by the Miragons, maybe, I guess. I have no idea what they're saying, and I really don't think it has much to do with finite elements. Or I really like the song that much, but I figured just to be in with the social media, let's turn it off here. Okay? All right. So let's get down to the really interesting stuff. So here I'm going to start doing some material on chapter 2, and this has to do with spring elements. You can read chapter 2 and get the background, but I'm just basically going to assume you've read through that stuff and take you through a particular problem and use the general approach outlined in chapter 1. Okay, so here's the problem we're going to solve. Okay, it's a 2 springs. These aren't elements yet. 2 springs. At one end they're fixed. At the other end, there's a 1,000-pound force acting to the right. And then in between the 2 springs, there's a 500-pound force acting to the left. The first spring has a spring stiffness of 1,000 pound-inches, and the second spring has a stiffness of 2,000 pounds per inch. Okay, so we're going to solve this using finite elements. All right, and we'll try to stick as much as possible to the general approach outlined in chapter 1, even though it's kind of simplified here, so it gets a little weird at some point in time. All right, so first step, right? Choose the element type and the discretization, okay? So spring element, right? We're going to use a spring element. And when I say spring element, it's going to have the following definition here, okay? We have a 2 nodes that are attached by this spring element, okay? The spring element has a stiffness K, and we can define a displacement at the 2 ends of the spring element, U1 and U2. So you can imagine these are going to be nodes 1 and 2 of this element respectively, okay? Now, we also have external forces applied to these nodes of the spring element at node 1 and node 2. And I know we always get this question, why does the force 1 act to the right when clearly it must act to the left because it balances out F2? Okay, that is true, but, well, I'll talk about it a little bit, but I have it on the next page. But basically, it's because we have to be consistent with how we define the internal forces and the external forces, right? And while this problem, it's obvious F1 is in the opposite direction of F2, if we have a much more complicated finite element mesh, okay, I can use the beauty of the camera here. Like if you look at something like this, and you pick one of those elements, it's going to be really difficult to figure out which way the forces should go to be in equilibrium. So instead, we just assume that the external forces are assumed in a positive state, so that they're positive in the x or positive in the y. Okay, so that's why this one's going in this direction. I'll mention more about that in a second. Okay, and here's the discretization. So the discretization is almost trivial. Obviously, this type of problem should be discretized with 2 elements, 3 nodes. You know, again, this is quite simple, but you have to remember if we have a part like this, the choice of the number of elements is, you know, less straightforward, okay? All right. Okay, so that's our discretization, all right? Now, coming up to here, I got my little blurb about, no. Why don't I explain it? I usually explain it here. Okay, well, let's just go back and explain this here. Well, it comes in the derivation, that's why. All right, so, external forces are always drawn in the positive direction for their axes, right? So for us, we're going to call this, in fact, the x direction, right? Everything happens in x. There is no y or z. It's a one-dimensional problem, right? So that's the x direction. This is positive x. So the external force at node 1 is drawn in the positive x direction. The external force at node 2 is drawn in the positive x direction, okay? So let's just leave it at that for now. All right. Step 2, right? Write the displacement field or the interpolation. So I have some, I used to have notes that kind of try to do this, but I think it's more confusing than it's worth. We'll see this much more clearly in chapter 3. So for now, I'm going to punt on this and just say it's not really applicable. Spring elements, especially when we talk about them in the context of like Nastran, they happen at a point, and so we don't really have an interpolation inside the element, okay? All right, so just deal with it for now, okay? It'll make more sense in the next chapter, as I said. Okay, step 3. Again, this is another one that makes a little less sense with regards to the spring element than with the elements in the subsequent chapters, but step 3 is to define the strain-displacement relationship and the stress-strain relationship, right? And so for a spring element, we don't really have strain or stress in a spring, but rather how much the spring stretches and then the force in the element to do that stretching, okay? So instead of a strain displacement relationship, we're going to talk about a stretch displacement relationship. And that's pretty obvious, right? You know, if this is your spring element, right? U1, U2, the amount that this element stretches, delta, is U2 minus U1, right? And the force in that element, now this is going to be an internal force, so the force is related to the stretch through Hooke's law, right? The force is the spring stiffness times delta. So if delta is positive, if you have a positive stretch, U2 greater than U1, you get a positive force, a tensile force. If delta is less than 0, the spring is in compression, maybe U2, well, U2 is less than U1, right? So you get a negative delta. Spring is in compression. The spring force in the element is also negative, right? It's a compressive element force, okay? Okay. So for this element, right, we're going to think of stretch as akin to strain and force as akin to stress, okay? All right. All right, so the next step, step 4, we need to derive the element stiffness matrix, okay? And so to do that, we're going to do direct stiffness, okay? Direct stiffness approach, all right? So what I've drawn here is a single element. This could be element 1 or element 2 for this problem. Or, you know, if you have 1,000 elements, it could be element 962, right? But this is the general stiffness matrix for an element, okay? So we have the element with its nodal displacements, U2 and U1. It has a spring stiffness K, and then also the external forces, F1 and F2, right? And those might be external forces either from actual, a combination of actual external applied forces to the problem, or this might be because this is connected to another element which is exerting an external force onto that element, okay? So, all right. So when we say direct stiffness, or I think the book actually calls this sum of forces, we do exactly that. We just write equilibrium on the two nodes. So we do sum of forces on node 1 as follows. Now here you can see, again, the external force acts in the positive x direction, and the internal force acts such that when it's positive, it's in tension, okay? So the external forces act positive with respect to the axis, you know, positive x or positive y. The internal forces are, their positive sense is such that their stress is positive, right? If it's in tension, it should be positive force or stress. If it's in compression, it should be a negative, right? So that's exactly the way we've drawn it here. On node 1, if this spring is in tension, right, obviously the internal force from the element is going to want to pull it to the right, right? So if we say this is node 1, and we have it in tension, it's going to pull it to the right, okay? F1 acts to the right as well because that's the way we've defined it. Now, it's just going to change sign, right? So the internal force is the spring stiffness times the stretch. And we know the stretch is U2 minus U1. So this internal force we can write as K times U2 minus U1, right? Acting in that direction. Likewise, we can do the same for the second node, right? And so here we have node 2. Here's the external force, again, acting to the right. But now the internal force is acting to the left, but that's because if this is the element and we're doing equilibrium at node 2, if it's in tension, right, the internal force is actually going to be acting to the left, all right? And that's what we have there. So this is the free body diagram, if you will, for node 2 and node 1. So, think about that force convention. We'll get questions on that often, I guess, right? So, right. So that is basically what I've summarized here in my notes, right? I always have to say this a couple times anyway. So again, what we got there was due to the fact that the external forces are always defined positive in their axis direction. So for us, we're just in X. So external forces, F1 and F2, act in the positive X direction. And the internal forces are always defined such that they're positive when they're in tension. Okay? All right. So, fine. So, well, I probably should show this picture again. Let's just do this, right? So, going back to it, maybe I can just do this real quick. So here are two free body diagrams, right? Can I get everything on one page? All right, that's not too bad. All right. So here's the free body diagram for the first node. So that just gives me F1 plus K times U2 minus U1 equals 0. Right? This plus this has to equal 0. And then we can just rearrange it to the following, right? K times U1 minus K times U2 equals F1. So that's just, massaging the equation and you get the following, okay? And you'll see why we write it that way. Now, we can also do the same for the sum of forces on the second node, all right? Now here, we have minus K U2 minus U1, right? Plus F2 equals 0, or putting that in the same sort of form where we put the forces on the right-hand side and the unknown terms on the left-hand side, we get minus K U1 plus K times U2 equals F2, right? So this becomes my system of equations. Right? This is my system of equations right there. Okay? Equation 1 and equation 2. So I have two equations for this element. And I actually have two unknowns, U1 and U2, so that makes sense. So we can write those two equations in matrix form as follows. Right? You can see they both have K's as the coefficients of U1 and U2. Just 1 and minus 1 it changes, so I pull a K out. Times U1, U2 equals F1, F2, right? So from the previous videos, you could probably, actually I didn't, I'll have to add that video, right? But I will add that video about solving, setting up linear systems of equations as a matrix vector multiplication, but you've seen that before in other classes, right? So these two equations, here's equation 1, written times its unknown, and here's equation 2, times the unknowns equals the right-hand side, okay? So this thing here, this right here, is the element stiffness matrix, okay? So that's what we call the element stiffness matrix. That's what we want to derive. This matrix system of equations are the equilibrium equations for that element, okay? All right. Okay, so that's step 4. Now we know what our element looks like. Right, we've done our discretization. We've derived the stiffness matrix, the element stiffness matrix, but now we need to do step 5, which is assemble the global stiffness matrix from the two element stiffness matrices in this case, okay? So here we go. So just to recall, here is our finite element model, if you will. 2 elements, 3 nodes. We have displacement at each one of the 3 nodes, U1, U2, U3. And then external forces. Again, all the external forces are written such that they're positive in the positive x direction. So F1 at the first node, F2 at the second node, F3 at the third node, right? So we want to find this global stiffness matrix that relates the unknowns U1, U2, and U3, that's the D vector, to the right-hand side vector, the external forces F1, F2, and F3. Okay? So how do we do that? All right? So that's what we're going to do now. Okay, there's several ways to do that. I always change what I do because I'm just that way. But since I'm doing videos, I guess I won't change it because this is stuck in videos. But I'm going to do it in this following approach, like it's kind of akin to a superposition, all right? And we'll in subsequent videos, I'll show the other 2 assembly approaches that we use, okay? But this one I think is kind of nice. Okay. Yeah. Okay. So if we take this the 2 elements and kind of split them apart, right? You can imagine I take this model and I split it up into 2 elements, right? So actually, you know, when I look at this, right, I put this superscript onto the forces to denote the element, right? So when I have a little circle on it, that means like it's an element, okay? So for this first element, right, we have the external forces as seen on the first element. So I have the superscript 1 here. Likewise, the same thing on 2. Now, obviously, these have to be equal and opposite for equilibrium, right? But that's what I have written there, right? So fine. I guess another way to state it is that F1 superscript 1 and F2 superscript 2 are the forces that are generated because of the stretching of the first spring. Likewise, these 2 external forces with the superscript 2 are the forces that arise due to the stretching of the second spring, okay? Okay. So there it is for now, okay? And if you want to think of it, these all have to sum up to satisfy equilibrium. So here we have a vector of forces due to the first spring, a vector of forces due to the second spring. These have to sum and equal the external applied forces, right? So now for the first spring, it's kind of obvious that F3 is equal to 0. Likewise, for the second spring, also F1 would be 0. You know, I can stretch the second spring, right? It doesn't really directly impose any force on the second node, on the first node, so to speak, okay? Likewise, I can stretch the second spring. Wait, no, I can stretch the first spring, and it doesn't really impose any force on the third node, right? Okay? But these are sort of the internal forces, okay? Due to the stretching of the spring. Right? All right. So, if we want to look at the internal forces due to the stretching of the first spring, well, we knew our stiffness matrix was I should probably put, actually, to be more correct, I should probably do it this way. Because we're denoting those as being the K's for the first element, right? And let me just excuse my interactive editing here, okay? All right. So what we're saying here is, right, so given the nodal displacements U1, U2, and U3, right, they give us the forces generated by the first spring, right? These are the ones that show up here, okay? These are the ones that we're talking about right here. Right? These are the forces that come about because we've stretched the first spring, all right? It's our element stiffness matrix that we derived in step 4, right? And you can see we've just expanded them with these zeros because the first element only relates to displacements at node 1 and 2 to the forces at nodes 1 and 2. Okay, but we've augmented it or expanded it out to put zeros here, so it's the same size as the global stiffness matrix. Okay, but you can see if I go back to can I get everything on the same page? You can see actually if this is the first element, we got a positive k1, a minus k1 times u1, and then minus k1 times u1, positive k1 times u2. Those equal the forces, right? So we've just expanded that with 0. So it's this equation here for the first element is exactly the same as this equation, right? It's just been expanded, if you will. All right. Okay. Now we can do the same for the second element. Okay. So here is our second element. And every time I go through this, I always think the other way is better. But like I said, I'll do direct sum of forces in another video. You'll see how that works. Okay, so again, here is our expanded stiffness matrix for the second element. But you can see it just populates the displacements of node 2 and 3 to the forces at node 2 and 3, right? There's no coupling between the displacement at the first node and forces at the first node, right? So we get zeros here, right? So basically we have the equation K2 times U2 minus K2 times U3 equals F2 minus K2 times U2, K2 times U3 equals F3. And again, to be correct, I should put superscripts here. So again, allow me to kind of fix this while I'm doing my notes. Notation's always a weird thing, so let's see if I can. Well, heck, other than the people that paid for the class, the rest of you are watching this video for free, so you get what you pay for, okay? So, but anyway. All right, so here are the stiffnesses from the second element, and this relates to the forces through the nodal displacements. Okay, so you can see this is, again, the force due to the stretching of the second element. Okay, this is basically the internal forces due to the stretching of the second element. All right? All right. So what we had before was a total sum of forces. So forces due to the stretching of the first element plus forces due to the stretching of the second element, plus if we had other elements they would add into here, they have to sum up and equal the external forces, okay? Okay. That's equilibrium, all right? Now, we can replace each one of these element internal forces with the appropriate KD. And now we're going to use the augmented one so it's the same dimension as the external force vector, right? And I think that's what I should have done here, right? So for us, it's going to be K1 times D plus K2 times D. So this is K2, and this one right here was the K1, okay? All right. So here we go, K1 times D plus K2 times D equals F, right? It's the same D, U1, U2, U3, all right? And so I can pull the D out, and you can see K1 plus K2 should be my global stiffness matrix. Obviously, I can write this as K, and now we have the form K times D equals F. So obviously, this has to be the global stiffness matrix already assembled, right? So this is telling me that actually just taking these augmented stiffness matrix for the first and second elements, and okay, so here again, I gotta fix this. This should have superscript 1, superscript 1, superscript 1, superscript 1, superscript 2, 2, 2, and 2. I think that'll be better. This is going to be a 1. This is a 1. Maybe this is why I didn't do this, because it gets a little weird here. This is a 1. This is a 2. This is a 2. This is a 2. And this is a 2. This is the reason why we always say, as instructors, that you should go through the derivations yourself just to make sure that they're all correct, right? So I don't have to. So get rid of those things. Okay, for those who are lucky enough to be in my class, I'll upload the PDFs of these final redacted notes. Okay. All right. There we go. Okay. So this is now okay. Sum of forces. This is going to be my total global stiffness matrix. Okay. So basically, we take this sort of stiffness matrix for the first element and the second element. We augment them with these zeros, add them together, and that gives me the global stiffness matrix. So, what justification do we have to do that? Well, again, maybe I didn't say it very well in this video. It's late on a Friday. But, right, we have the two elements split up. So let me just go over this really quickly, right? So here are the forces due to the stretching of the first element, the forces due to the stretching of the second element. We can write them in the following form, right, as a column vector, okay? Now, these forces are due to the stretching of the element, so this is the KD equals F, if you will. So when we just consider the first element, right, this is going to be the forces due to the stretch of the first element. Likewise, I should have done it, like whiteouts sticking together. Likewise, here are the forces due to the stretching of the second element. They have to all sum together to give me the total force, or balance with the external forces. So now we can take each F due to the stretch of that element, break it up into KD for that particular element, right? Pull out the D's, and you can see that the global stiffness matrix has to come about just from the sum of these augmented stiffness matrix. We're padding them with zeros, right? And so what you can see here is it's kind of interesting. It kind of makes sense, and we'll see this more when we look at the other approaches. The only place that they overlap is on the second row, second column. That's where node 2 is, right? And that is because the springs are connected to each other at node 2, right? So this is the global stiffness matrix, and we can put in the actual numbers here for the element stiffness. Remember, the first element is a stiffness of 1,000, the second element of 2,000, and that gives us the final stiffness matrix to be as follows. And right, obviously, I shouldn't be so careless. This has units of pounds per inch. Okay, pounds per inch. Okay, so that we've assembled the global stiffness matrix. All right, let's keep going. This is kind of a long video. Usually I break this up, but you can pause here if you want. But maybe I should play that annoying video again. But anyway, so here we go. Step 6. So now we have our assembled global stiffness matrix, okay? And we have our displacements and our external forces, okay? So now we have to solve the system for the displacements. Before I go any further, let's talk a little bit about this external force on the right-hand side, okay? Let's go back to the picture we had of our problem, right? Let's go back to this. Okay, remember this was the original problem, okay? So here are the external forces, okay? Well, clearly at node 2, this is clearly at node 3, this one, we have a force acting in the right of 1,000, so that's a positive 1,000, so there we go. At node 2, we have a 500-pound force acting to the left. That's in the negative x direction, so that's going to be a negative 500 pounds. And at node 1, there is an unknown reaction force. Because this problem is fixed at node 1, there has to be some force acting at node 1 that constrains it so it doesn't move. All right? That's a reaction force. It's F1. Okay? It's unknown, although I know there's people out there that are going to look at this and say, clearly, it has to be 500 pounds acting to the left, or a minus 500 pounds, right? So yes, that's true. You're getting that by just equations of statics, but let's treat this in the most general way again, because we're doing finite elements. And again, to bring back this picture, When you have a more complicated problem, it's difficult to figure out what those reaction forces should be, right? So, although in this problem it's easy to see the reaction force by inspection, in general it will not be, okay? So we're going to leave this as an unknown F1, okay? All right. All right, but we do know one other thing, right? We know that even though we know that we don't know the reaction force at node 1, we do know that the problem is fixed, so we know that the displacement U1 at that node is equal to 0. Right? So this is always going to happen. This is what I mean when I say we have to solve KD equals F with the displacement constraints, okay? So this thing that the displacement at the first node is 0, that's what we call a homogeneous displacement boundary condition. We could have prescribed that node 1 moves a certain amount, like a half inch, right? That would be an inhomogeneous displacement boundary condition, right? It's homogeneous because the right-hand side is 0. If the right-hand side were not 0, it would be inhomogeneous, okay? And we'll use that terminology later on. But right now, we have that one, okay? Another interesting thing to note about this problem is, if you just look at this stiffness matrix by itself, as it stands now, right? So this is the global stiffness matrix, K. This is the unknown displacement vector, D, and this is the right-hand side external forces, F, right? So if you look at K by itself, its determinant is 0, right? So you can go through and take the determinant of this matrix. It's you'll see that. Well, it turns out to be 0. Okay. The easiest way to see that, right? When we've talked about this before, when this matrix has a 0 determinant, that means there's a linear dependency. There's no unique solution. Okay. In this case, you can see the linear dependency clearly. If we add up, if we take equation row 1 and row 2 and add them together, you get row 3, right? So row 3 equals row 1 plus row 2. So there's the linear dependency, right? That means that you cannot find an inverse to K. There's no unique solution. Either there's no solution or there's an infinite number of solutions. In this particular case, there's an infinite number of solutions, okay? The reason why we have no unique solution is, as it's described up here, without respect to this boundary condition, if we just consider this problem here, described by KD equals F, it allows rigid body motion, okay? And so let's talk about that a little bit. So here's a little bit of an aside, right? Let's just go through this aside. So excuse me for going off on a tangent. We'll come back to solving problem 6 in a second. But this is very important with regard to practically solving finite element problems. Okay, let's just look at any particular element, right? So let's say here's a K of 1,000 pounds, and now I'm going to use like mechanics, materials stuff for statics, right? 200 pounds to the right, it means there's 200 pounds to the left, stretches the spring, goes in tension, right? So the force in the spring is 200 pounds, right? You can section it wherever you want. You can see it's 200 pounds in tension. The elongation, or the stretch, has to be F over K, so 200 pounds divided by 1,000 pounds per inch. So that gives me a stretch of 0.2 inches, right? And now we say, fine, what's the displacement at node 1 and node 2? What's the displacement at here of U1 and here of U2, right? Well, there is no way you can solve for that. There is no way you can solve for that, right? Clearly, U1 could be 0 and U2 could be 0.2 inches. That would satisfy the stretch and the forces, right? That is a solution. But you can also have U1 of negative 0.2 and U2 being fixed at 0. This is basically the same thing, but the string stretching this way. So obviously you could have the spring stretch to the right, 0.2 inches, to the left, 0.2 inches. They both satisfy these mechanics and materials equations, right? Or you could do other things. You could, half to the right, half to the left, or whatever, right? So what's going on here? Well, the spring stretches this amount. By just defining the forces, you get the forces in the stretch uniquely, but you do not get the displacements uniquely. Okay, so this is always going to happen with finite elements, right? Until we prescribe the displacements, the fixation of the nodes, we will not be able to uniquely solve for the displacements. We can uniquely solve for the stresses and strains using like mechanics and materials approaches, but not the displacements, okay? So that's the problem here. So when I go back up to this, all right, the problem here is, right, oh, I should say this. When I look at this system of equations, it doesn't say anything about how the spring is fixed. It doesn't tell me that the left endpoint of this spring problem is fixed, okay? I need to somehow solve this with respecting the fact that U1 is equal to 0. Now, once I say that U1 is equal to 0, right, fine. Now we can, we've eliminated the rigid body mode, and then the spring system will just stretch off to the right, okay? All right, so that's a big deal, okay? So we have to solve KD equals F, but respecting the displacement constraints, okay? In this particular case, it's that U1 has to equal 0, all right? Okay. So how do we do that? All right, how do we do that? Well, let's go back to step 6, okay? So we're going to solve for this problem, right? So if you look at what we got here, we know that U1 is equal to 0. We don't know F1. So really we need to solve this system for U2 and 3 and F1. Right? We have 3 equations and 3 unknowns. So obviously one thing you can do is you can just manipulate these. You can just go algebraically like you would, in a basic matrix algebra class, and write the equations back out and solve for F1, F2, F3 by just, algebraic manipulations. That's fine. But when you have millions of equations or hundreds of thousands of equations, you don't really like computers to do algebraic manipulation. So let's find a more general way to do this, okay? So again, there'll be a couple of ways of doing this, but I'll solve it with a simple way when we have homogeneous displacement conditions, okay? So if you look at this, we got the 0 here, right? We got that because we've set U1 equal to 0. Okay, well, what's going to happen? Well, that 0 is going to get multiplied by this 1. It's going to get multiplied by this -1 and by this -0. So, the effect of these things is going to just zero out, right? So if you look at like this second equation, right, it's going to be 0 plus 3 times U2 minus 2 times U3. Likewise, this third equation is going to be 0 times minus 2 times U2 plus 2 times U3 equals 1,000, okay? So really, this system of equations is equivalent to this reduced system of equations, okay? So this is the approach that the book uses, and so this will be the approach that I use. Again, there's a couple other ways of doing this. So when we have homogeneous displacement boundary conditions, and we'll change this for inhomogeneous too, we'll do the same. We're going to actually solve this reduced system of equations. So we're solving effectively this system of equations, okay? All right, that's the reduced system. Because the zeros knock out this first column, all right? Okay, the nice thing about that is now I have a stiffness matrix times a vector of unknowns equal to the right-hand side that's all known, right? I don't deal with this F1 being unknown on the right-hand side and a 0 known on the left-hand side. So this is a nice thing for a computer to solve. And in general, we'll solve these in MATLAB. The other thing you'll note, okay, so we're going to call this the reduced system. So that's terminology you guys have to know. When I say on an exam, write the reduced system, this is what I mean, all right? And I'll put little overbars on it to denote that it's a reduced system. Okay, the nice thing to know about this is now you actually can solve the system. If you look at the determinant of this reduced matrix here, it's not 0, it's 2,000 pound-inches, right? It's 6,000 minus a minus 4,000, so it's 2,000 pounds per inch. It's not equal to 0. So the inverse exists. There is a unique solution to that, okay? And so you can just see, here's just the math. I go through it. I take the the two equations and just divide by 1,000, add them together, and I get U2 is equal to 1/2 of an inch. Then take that, put back in the second equation, and get that U3 is 1 inch. So that's my solution. The displacement at the second node is 1/2 of an inch to the right, and the displacement at the third node is 1 inch to the right. Okay, so that's my solution, and I got it from this reduced system. Okay, so basically, wherever you have a homogeneous boundary condition, you kind of cross out the row and the column, and you're just left with that reduced stiffness matrix, and that's what we're going to solve. Okay, we still need to find the reaction force. Sometimes we don't really care, but usually it's of interest. So how do we go back and find the reaction force, F1? All right? Okay. Well, let's look at the system we had before, right? So this was our original stiffness matrix. Now actually I know the displacement D. I know it's 0, I know it's 1/2, and I know it's 1. And that has to equal the external forces, okay? So actually F2 and F3 we already did know. It's minus 500 and 1,000. But this first equation actually is going to allow me to find F1. So F1 has to be equal to 1,000 times 0.5 minus 1,000 times 1. All right? So just that's the first equation, right? It's going to give me F1 is 1,000 times 0 minus 1,000 times 0.5. So that's what we get here, and that's equal to minus 500, right? That's what it comes out to be. So that is F1. That's the external reaction force, okay? So a more general way is you can always find the external reaction forces by taking the original full stiffness matrix, multiplying it by the solution. Now, where you had a displacement constraint, you will get the reaction force. At the other nodes, you should get the external forces. And that's an equilibrium check, okay? So if you take this stiffness matrix and multiply it by this vector, you'll see that you get minus 500 here, minus 500, and 1,000. And you can do that if you want, right? And you can see that we recover the reaction force at F1 as well as checking equilibrium at the second and third nodes, okay? And that's just basically what I'm saying here. So that makes sense, right? Minus 500, minus 500, 1,000, right? So that satisfies equilibrium. That's what you would think would happen, okay? So that's good. All right. So, and that's basically what I was saying. So there you go. We got our solution. We used step 6, right? In general, you have this global stiffness matrix that's singular. You solve that respecting the displacement boundary conditions. These are to eliminate the rigid body motions. Okay, that will give us a reduced system that you can solve for the displacements. Then to get the external reaction forces, you go back and you multiply the known solution D by the original full stiffness matrix, and that'll give you the reaction forces, as well as checking equilibrium on the other forces, okay? So just to, those steps again, right? Find the reduced system, solve for the displacements, take the displacements, multiply by the original stiffness matrix, and that'll give you the reaction forces. All right. Wow, we're almost there, okay? So step 7. Step 7 and 8 are pretty easy in this case. Find the element strains and the element stresses. So for a spring, as we mentioned before, this is going to be the stretches and the forces, right? Stretches like strain, forces like stress. So the way we do that is we go back to the original element stiffness matrix, right? The original strain, displacement, stress strain relationships from step 3. Right? Let me just make sure I get that right. Step 3. Where was step 3? I've only been using this text for a semester, so. Right. We're going to go back to step 3 and use the stretch displacement relationship and the force stretch relationship to get the element stretches and forces, right? So for the first element, the stretch is just going to be U2 minus U1. U2 is 1/2 of an inch. U1 is 0. So that means that the first element stretches by a positive 1/2 of an inch, right? So it's stretching by 1/2 of an inch. The force is going to be the element stiffness, which is 1,000 pounds per inch, times that stretch, the half of an inch. So that's 500 pounds. Again, positive, that means it's the tension. And we do the same for the second element. Now the stretch in the second element is going to be the displacement at the third node minus the second node, right? Right. Second element, the stretch is the displacement at the third node minus the displacement at the second node, right? Okay. So that's a half of an inch as well, but its spring stiffness is 2,000 pounds. So when we go back and find the spring force in the second element, it's 2,000 pounds times that half of an inch. So that gives me 1,000 pounds of force. Okay. Okay. And so the last step is to step 8. Interpret the results. Okay. So usually this is going to be like if we're designing the spring system, are the forces in the springs too much? Does the spring stretch too much? That sort of stuff, right? So is it appropriate for our design, right? A lot of times in this class, we're going to be looking at these problems from the context outside of a design process. In which case, when I talk about interpreting the results, as you always have to do anyway, one of the first questions is, do these results seem to make sense? Do they seem correct? Now, for these problems, it's going to be relatively easy to figure out, right? Okay, focus. Let's see if we can focus. Why is this not focusing? Yeah? Okay, this. Okay, I don't know what's going on. Why is it not focusing? Okay, we're almost done anyway. I'll just go through it. It'll try to do it sooner or later. Oh, that's terrible. There it goes. It went for a second. Okay. Do the results make sense? So one of the easiest ways to do that is to just check equilibrium, which we already basically did. So we checked equilibrium on the total system, and that worked out, right? The reaction force balanced the other two external forces, right? So equilibrium's checked on the whole finite element model. We can also check equilibrium. Well, there it is right there, right? That's the sum of forces, right? You can see that. Right? The other way we can check equilibrium is check equilibrium on each of the elements. And this also has to be satisfied, right? So if we look at the first element, there's an external force of 500 pounds. This is the reaction force, actually, left at node 1. And that has to balance the internal force, the force in the element. This is the force we found in the previous step, in step 7. That was 500 pounds in tension, so it's acting to the right. So that checks, okay? And we can do the same for the second element. I chose to cut it here in the middle of the second element to expose the 1,000 pounds, and the internal force of that is 1,000 pounds. Like if you wanted to really check it, you could also check it, like this way, right? So here's the first element, and then here's the second element, taking the cut from the left. Here is F2, if you will. Here we have the 500 pounds from F1, right? And then also F2, which is equal to 500 pounds. Well, I should say it's a negative F1, negative F2, right? And the reaction force we found from step 7 was, the element force we found from step 7 was 1,000 pounds. So here you can see the 1,000 balances the two 500s, right? So again, that element is in equilibrium, all right? So that checks out. There are other ways we can check our solutions. We'll talk about that at different points in the class, but that's basically it. Okay, so what's important in this, right? We use the 8 steps. It's a bit long-winded, but make sure check step 4. That's a very important step, right? How we derive the element stiffness matrix. Also, step 6, how we solve using the displacement boundary condition. Very important. Step 7, recovering the elements stretches and strains, or in this case, forces and stretches. Very important as well. People will try to back those out by other approaches on exams, and you have to do it the finite element way, which is the way I showed in this video in step 7. Okay? All right. That's the end of this. I hope you made it through without staying awake, with staying awake. And so the video's over, so we will use our outro music.